Hello, this is a reporting about work, study, and measurement, specifically Chapter 5, which is Workplace, Equipment, and Tool Design. Its primary objectives is to fit the workplace to the operator, provide adjustability, maintain neutral postures such as joints in mid-range, minimize repetitions, use power grips when force is required, and use pinch grips for precision and not force. The topic outline for Chapter 5, Part 1, which is Anthropometry and Design, are design for extremes, design for adjustability, design for average, and lastly is practical considerations. In Part 1, Anthropometry and Design, the primary guideline is to design the workplace to accommodate most individuals with regard to structural size of the human body. Anthropometry is rooted from the word anthros or anthropos, which means man and human, and meter, which means to measure. Anthropometry is the science of measuring the human body and is termed anthropometry and typically utilizes a variety of caliper-like devices to measure structural dimensions. Examples of which are stature and forearm length. Practically speaking, however, few ergonomists and engineers collect their own data because of the wealth of data that has already been collected and tabulated. Close to 1,000 different body dimensions and for close to 100 mostly military population types are available in somewhat dated anthropometric source book, which is according to Webb Associates in 1978. More recently, the CASER, or is an abbreviation for Civilian, American, and European Surface Anthropometry Resource project, collected over 100 dimensions on 5,000 civilians using three-dimensional body scans. A summary of useful dimensions that apply to the particular postures needed for workplace design for U.S. males and females, given in this table. And these are the selected body dimension lists. The use of this selected body dimension list is to know the standard of the positioning of the joints to maintain neutral postures. Much of this anthropometric data is included in computerized human models such as CombiMan, Jack, Mannequin Pro, and SafeWorks that provide easy size adjustments and limitations in ranges of motion or visibility as part of the computer-aided process. This is a selected body dimensions and weights of U.S. adult civilians, listed 16, where X is equals to the weight, and that is based from the selected body dimension list, or this diagram shown. These parts were actually surveyed and were taken off from a specific population and was measured to gain an average of the 5th percentile, the 50th percentile, and the 95th percentile. But the goal here is to know the minimum, which is the 5th percentile, and the maximum, 95th percentile, of the stature or postures, body dimensions that are observed in a specific population. Now, shown is a standard normal distribution of male weight, where the 5th percentile or the negative Z score is at the left side and the positive Z score or the 95th percentile is at the right side. Z score or standard curve technically measures how many standard deviations below or above the population mean a raw score is. An example is as shown. A kth percentile is defined as a value such as k% of the data values, or plotted in ascending order, are at or below this value, and 100 minus k% of the value are at or above this value. A histogram plot of U.S. adult male statures show that bell-shaped curve termed as normal distribution within a median value of 68.3, which is shown earlier in the figure or table 5.1. This is also the 50th percentile value. For example, one half of all males are shorter than 68.3, while one half are taller. The 5th percentile male is only 63.7 in tall, while a 95th percentile male is 72.6 in tall. The proof is as follows. Typically, in a statistical approach, the approximately bell-shaped curve is normalized by the transformation given below. Z is equals to quantity of x minus the Greek symbol mu. Typically, in a statistical approach, the approximately bell-shaped curve is normalized by the transformation given below. Z is equals to the quantity of x minus the Greek symbol mu all over delta, where mu means the mean and the delta means standard deviation, or the measure of dispersion. Now, to form a standard normal distribution, once normalized, any approximately bell-shaped population distribution will have the same statistical properties. This allows easy calculation of any percentile value desired, using the appropriate k and z values as follows. So, in the kth percentile, when you're using the 10th or the 90th percentile, your z value would be positive negative 1.28. When your kth percentile is at 5 or the 5th percentile or 95th percentile, the z value is positive negative 1 plus 1.645. If the percentile is 2.5th or 97.5th percentile, the z value would be positive negative 1.96. And lastly, if your percentile would be 1th or 99th, z value would be positive negative 2.33. Now, given that the measure stature for males in the US is 68.3, and that is according to this table, in the stature, the 50th percentile, the 5th percentile, and the 95th percentile. While the standard deviation is 2.71 given, or 6.9 cm, according to Webb Associates in 1978, the 95th percentile male stature is calculated as 68.3, which is our 50th percentile of the male stature, plus the 1.645 z score, or the z value, times 2.71, which is the given standard deviation. And it is equals to 72.76 inch, which is close to our table in the stature 95th percentile, which is 72.6. While the 5th percentile male stature is 68.3, the fifth according to the 5th percentile, minus 1.645 times 2.71, which is the standard deviation given, and it is equals to 63.84, which is closely relative to our table in the stature height in the 5th percentile, which is 63.7. Now, we're going to look at the normal distribution curve, which is below this. Now, as you can see, the figure below is closely related or identical to the standard normal distribution of male weight. Shaded area of the left side is 5% as well as the right side. And the left side is the 5th percentile, while the right side is the 95th percentile. And note that the calculated values of 72.76 and 63.84 are not exactly equal to the actual values in the table, which is 72.6 and 63.7 inches. This is also because the US male height distribution is not a completely normal distribution.
Design for extremes. Designing for most individual is an approach that involves the use of one of three different specific design principles as determined by the type of designed problem. Design for extremes implies that a specific design feature is a limiting factor in determining either the maximum or minimum value of a population variable that will be accommodated. For example, clearances such as a doorway or opening into a storage tank should be designed for the maximum individual, that is, a 95 percentile male stature or shoulder width. The 95% of all males and all most females will be able to enter the opening. Obviously, for doorways, space is usually not at a premium, and the opening can be designed to accommodate even larger individuals. On the other hand, added space in military aircraft or submarines is expensive, and these areas are therefore designed to accommodate only a certain or smaller range of individuals. Reaches for such things as a brake pedal or control knob are designed for the minimum individual, that is a 5 percentile female leg or arm length. The 95% of all females and practically all males will have a longer reach and will be able to activate the pedal or control.
Next up is design for adjustability. So it is typically used for equipment or facilities that can be adjusted to fit a wider range of individuals. It also ensures the workstation fits the worker, and it recognizes uniqueness to every worker or employee to meet their individual needs. And designing for adjustability is the preferred method of design, but since it is adjustable, so it is quite expensive for the implementation of it. So example would be chairs, table, desk, vehicle seats, steering columns, and tool supports are devices that are typically adjusted to accommodate the worker population ranging from 5th percentile females to 95th percentile males. And another example for this one is the driver's seat car. So the height, position, tilt, angle, back support are all adjustable so that it can provide comfort to the user. The next design would be the design for average. So unlike the design for adjustability, design for average is the cheapest but least preferred approach. Even though there is no individual with all average dimensions, there are certain situations where it would be impractical or too costly to include adjustability for all features. So this design for average, their approach is like one size fits all solution. And the example for that one would be most industrial machine tools are too large and too heavy to include height adjustability for the operator. And another example for this one is your typical public transportation. If you're gonna take the bus or the jeep when you're gonna commute, as you can observe, the seats are identical, same length, same distance, and all. And so average person doesn't exist. We all know that we are distinct from one another, especially when it comes to body dimensions. So it vary from person to person, and if, designing for average can accommodate maybe 50% of the users, but it is not optimal for everyone. Maybe it's okay to sit in an uncomfortable seat for 15 to 30 minutes when you're commuting, but when it comes to industrial workplace or environment, it is really vital to be comfortable. And because a fixed workstation would cause repetitive stress to the employee or the worker if they're working every day.
So the last part of our report is the practical considerations. Due to the passage of the Americans with Disabilities Act of 1990, reasonable effort must be made to accommodate individuals with all abilities. So the special accessibility guidelines have been issued by Department of Justice of 1991 regarding of the parking lots, entryways into buildings, assembly areas, hallways, ramps, elevator, door, lavatories, restaurant or cafeteria facilities, alarm and telephones. And it is also very useful if practical and cost effective, since to build of a full mock-up sa equipment being designed and then have the users evaluate the mock-up. Anthropometric measurements are typically made in standardized posture. In real life, people slouch or have relaxed postures, changing the effective dimensions and the ultimate designs. An example in 5.2, the final design should accommodate more than 95% of the population so that the makaless sa errors during production, and the true design should have used body dimensions for a combined sa male and female population. However, the combination data are rarely available, but the data can still created through statistical techniques.
Good afternoon, everyone. I am Rachel Efren, and I'm here to discuss the part 2, which is the principles of work design, the workplace. The first lesson would be determine work surface height by elbow height. The work surface height should be determined by a comfortable working posture for the operator. Typically, this means that the upper arms are hanging down naturally and the elbows are flexed at 90 degrees so that the forearms are parallel to the ground. In figure 5.4, we can see that the upper arms are hanging down while the elbows are flexed at 90 degrees so that the forearms are parallel to the ground. The elbow height becomes the proper operation or work surface height. If the surface is too high, the upper arms are abducted, leading to shoulder fatigue. If the surface is too low, the neck or back is flexed forward, leading to back fatigue. It is important to have a good posture in doing your work so that you will not encounter any problems while doing it. For the second lesson, adjust the work surface height based on the task being performed. This means that your work surface height will be basing on the task that you are doing. For rough assembly involving the lifting of heavy parts, it is more advantageous to lower the work surface by as much as 8 inches or 20 centimeters to take advantage of the stronger trunk muscles. For fine assembly involving minute visual details, it is more advantageous to raise the work surface by up to 8 inches or 20 centimeters to bring the details closer to the optimum line of sight of 15 degrees. Another, perhaps better, alternative is to slant the work surface approximately 15 degrees, then both principles can be satisfied. However, rounded parts then have a tendency to roll off the surface. So in here, we can see that when you lift a heavy object, they need to lower the work surface as much as 8 inches so that they can take advantage of the trunk muscles. Then, when they are involving minute visual details, it is advantageous to raise the work surface by up to 8 inches, so they need to raise it up and bring the details closer to the optimum line sight of 15 degrees. So we can see here that the line sight of the person in the picture is at 15 degrees angle. These principles also apply to a seated workstation. A majority of tasks, such as writing or light assembly, are best performed at the resting elbow height. If the job requires the perception of line detail, it may be necessary to raise the work to bring it closer to the eyes. So basically, the most important thing is the operator is comfortable in his or her position while doing the work so that they can perform the work better and have no problems while doing the task. Seated workstations should be provided with adjustable chairs and adjustable footrest. So we can see here that the chairs can be adjustable and the footrest as well, because it will depend on the height also of the operator on how he or she can grab the things that he or she is working on. Then we need to adjust it to make them comfortable in doing their task. Ideally, after the operator is comfortably seated with both feet on the floor, the work surface is positioned at the appropriate elbow height to accommodate the operation. Thus, the workstation also needs to be adjustable. Short operators whose feet do not reach the floor, even after adjusting the chair, should utilize a footrest to provide support for the feet. So that's what I'm telling you about a while ago, that it also depends on the height of the worker. If they cannot reach the floor, we need to use a footrest so that they have a support for their feet.
And this is all about provide a comfortable chair for the seated operator. So first of all, before we're going to start, I just want to explain about sitting. So sitting, there's actually sitting postures are actually very important because it improves blood flow, it helps keen your nerves and blood vessels, and it supports your muscles, ligaments, and tendons, especially to those people who are actually working in the operation. And right now, let's go to the next slide, and this is the seated posture is important from the standpoint of reducing both the stress on the feet and the overall energy expenditure. Because comfort is a very individual response, strict principles for good seating are somewhat difficult to define. So as what I have discussed a while ago, sir, so this is all about being comfortable while you are working. So it's very important since most of us, when you're going to go to the operation sites, you could see the workers or operators sitting, and I do believe that sitting postures or how comfortable they are when they work, it's very essential to their health and to their bodies. And furthermore, few chairs will comfortably adapt to the many possible seating postures. So right now here, let's have a look here in the figure 5.7. So this is the 6 basic seating postures. And the first one is the front support. So you could see there that there's actually a frontal here, so that's why it's called front support, because it actually supports your front body while you are working. And next would be the reclining. So it is obvious here that the operator is actually reclining, so he or she is reclining on the chair. And the next is the kneeling part. So in this part, the operator is also kneeling, like you can see on his knee. And the next one is the rebalance. So it is actually a seating posture where you can balance or you can rebalance. And the next one would be the stool. So it's like sitting on a stool. So this is actually the posture of it. And the last one would be traditional. So traditional is the most common one, since we kind of, most of us kind of sit like this. And now let's have the next one here. So however, several general principles hold true for all seats. When a person is standing erect, the lumbar portion of the spine curves naturally inward, which is termed lordosis. So, however, as a person sits down, the pelvis rotates backward, flattening the lordotic curve and increasing the pressure on this in the vertebral column. So, therefore, it is very important to provide lumbar support in the form of an outward bulge in the seat back, or even a simple lumbar pad placed at the belt level. So in this spot here, so lumbar supports actually maintain a natural curvature without lower back support. So overall, it actually supports um, our lumbar part of our body, and it is it is actually put like chairs, existing chairs, like for example, like um on the chairs there, sir, so it can support the lumbar. And right here, let's take a look on the figure 5.8, and this is the posture of the spine when standing and sitting. So lumbar portion of spine is lordotic when standing. So that is this one, the letter A, and this is kyphotic when sitting, and this is the letter B. So the shaded vertebrae are the lumbar portion of the spine. And here, let's have another approach to preventing flattening of the lordotic curve is to reduce the pelvic rotation by maintaining a large angle between the torso and thighs. And you can see that one here again on the kneeling posture here on the 6 basic seating posture. So this is actually a good position for preventing flattening of the lordotic curve. And this theory is that this is a shape maintained by astronauts in the weightless environment of space. So this is the one. It's actually like a representation of the theory about how we can maintain our shape in the weightless environment of space. So this one here. And furthermore, however, the disadvantage of this type of seat is that it may put additional stress on the knees. So as we all know, it's like kneeling, so it would actually really put pressure. The addition of a pommel to the forward sloping seat, forming a saddle-like seat, may be a better overall approach as it eliminates the need for knee supports and still allows for back support. And now here, so this is actually an example of a saddle chair. So saddle chair is actually used the same principles in its design as an equestrian saddle. So in this part here, this is the version of a saddle chair, and it actually improves leg circulation and reduces fatigue. So as an ESL teacher, I have this kind of chair, and I usually use this when teaching in the office, and it actually makes me more comfortable and not so much pressure on my back. And now this is also the designing seating in a large training room. So in this spot here, this example will show the step-by-step procedures utilized in a typical design problem. And number one is determining the body dimensions critical to the design, such as sitting height, erect, and high height sitting. Number two would be define the population being served. So US adult males and females, it depends on the population that you have chosen. And next would be the number three, select a design principle and the percentage of the population to be accommodated. Number four would be find appropriate anthropometric values from table 5.1. And number five would be add allowances and test. So this is actually a seating design in a large training room. And now let's have the next one here. This is the recommended seat adjustments on table 5.2. So you can see here that these are the seat parameter here. So seat height, seat depth, seat width, and so on. And these are the design value in centimeter. And for example, let's have the seat height number letter A, and it actually has 16 to 20.5. And the comments would be here. So it would be too high, compresses thighs, too low, and this pressure increases, and that would be so on.
Next is 5.2.4, provide adjustability in the seat. Adjustability for specific seat parameters. Seat height is most critical, with ideal height being determined by the person's popliteal height, which is defined in the figure below. As you can see in the figure below, popliteal height is the distance from the underside of the foot to the underside of the thigh at the knees. Table 5.1 shows selected body dimensions and weights. In this table, you can see body dimension,
the sex or the gender, the dimension in inch, and the dimension in centimeter. For example, eyesight. For the male, it's 59.5 inch, and for the female, it's 54.4 inch. As it that is too high will uncomfortably compress the underside of the thighs. As it that is too low will raise the knees uncomfortably high and decrease trunk angle, again increasing this pressure. So it must be that the chair is adjustable so that the operator, may it be tall or short, can sit comfortably. Specific recommendations for seat height and other seat parameters are given in the table 5.2. Table 5.2 shows recommended seat adjustment ranges in which you can see seat parameter, design value in inch or centimeter unless specified, and the comments. In addition, armrests for shoulder and arm support and footrest for shorter individuals are recommended. Casters assist in movement, and ingress, which is going or entering, or egress, which is going out or leaving from the workstation. However, there may be situations where a stationary chair is desired. An overall optimum working posture and workstation is shown in the figure 5.10. Figure 5.10 shows properly adjusted workstation for the arms, backrest, posture, desk, telephone, screen, keyboard, document holder, seat, feet, and avoiding eye strain. So the next is 5.2.5, encourage postural flexibility. It is important to encourage postural flexibility in the workplace. The workstation height should be adjustable so that the work can be performed efficiently, either standing or sitting. Because our human body is not designed for a long period of sitting or standing. If we sit in a long period of time, we may feel some back pain, or if we stand in a long period of time, we will surely have cramps and muscle pain, because the discs between the vertebrae do not have separate blood supply, and they rely on the pressure changes resulting from movement to receive nutrients and remove waste. And postural rigidity also reduces blood to the muscle and induces muscle fatigue and cramping. That's why an alternate compromise is to provide a sit-stand stool. So what is sit-stand stool? So sit-stand stool are chairs and stools allow you to shift your weight and rest periodically while standing, so you can stand longer. Perch sitting is great blend between sitting and standing for you to have some support while standing without being in a fully seated position. So there are two key features for a seat or stand stools are height adjustability and a large base of support so that the stool does not tip, preferably long enough that the feet can rest on and counterbalance. So here we can see in the figure 5.11 the industrial seat or stand tools. So the seat stand stool are height adjustability, so we can adjust its height to the preferred length that we desire.
Provide anti-fatigue mats for standing operator. So what is anti-fatigue mats? Are mats designed to reduce fatigue caused by standing for long periods on a hard surface. Example, cement floor. So anti-fatigue mats are often used to decrease foot and lower limb disorders for workers who stand in one position for long periods of time. Standing for extended periods on a cement floor is fatiguing. When we say fatigue, something such as tiring efforts or activity that causes tiredness or weariness. The operators should be provided with resilient anti-fatigue mats. The mats allow small muscle contraction in legs, forcing the blood to move and keeping it from tending to pull in the lower extremities.
Let's talk about locating all tools and materials within the normal working area. In every motion, a distance is involved. The greater the distance, the larger the muscular effort, control, and time. So, it is therefore important to minimize distances. Positioning of our body and equipment in a workplace is very important so that the worker can do work comfortably. Arms. When an operator hands are on keyboard, Upper arm and forearm should form right angle. Backrest, adjustable for occasional variations. Shape should match contour of lower back, providing even pressure and support. Posture, sit all the way back into chair for proper back support. Neck should be comfortably erect, knees should be slightly lower than hips. Desk, thin work surface to allow legroom and posture adjustments. Adjustable surface height preferable. Table should be large enough for books, files, telephones, while permitting different position of screen, keyboard, and mousepad. Telephone. Cradling telephone receiver between head and shoulder can cause muscle strain. Headsets allow head, neck to remain straight while keeping hands free. Document holder. Same height and distance from user as the screen, so eyes can remain focused as they look from one to another. Screen. Position so that mid-screen is 150 down from eye level. Keyboard. Position to allow hands, forearms to remain straight, level. Seat. Adjustable height, angle, firm cushion, waterfall, front helps circulation to legs. Feet. Entire sole should rest comfortably on floor or footrest. Here are the tips to avoid eye strain. Number 1. Get glasses that improve focus on screen. Measure distance before visiting eye doctor. Number 2. Try to position screen or lamps so that the lighting is indirect. Do not shining directly at screen or into eyes. Number 3. Use a glare reducing screen. Number 4. Periodically rest eyes by looking into the distance. The normal working area in the horizontal plane of the right hand includes the area circumscribed by the arm below the elbow when it's moved in an arc pivoted at the elbow. This area represents the most convenient zone within which motions may be made by that hand with the normal expenditure of energy. The normal area of the left hand may be similarly established, since movements are made in a third dimension as well as in the horizontal plane. The normal working area also implies to the vertical plane. Generally speaking, all work materials and equipments should be in the range of the worker so that the worker can work comfortably in a working area.
Next is fixed location for all tools and materials to permit the best sequence. So in driving an automobile, we are all familiar with the short time required to apply the foot brake. So the reason is very obvious since the brake pedal is fixed cat iron, no time is required to decide where the brake is located. So the body responds actively and applies pressure to the area where all driver knows the foot pedal is located. So if the location of the brake foot pedal varied, the driver would need considerably more time to brake the car. Similarly, provide fixed location for all tools and materials at the workstation eliminates or at least minimizes the short hesitations required to search for the objects needed to do the work.
So for the next topic, use gravity beams and drop delivery to reduce reach and move times. So gravity beams are components that can be continuously brought to the normal work area, thus it will eliminate long reaches to get supplies. So for basically, gravity beams are the containers which provide the workers all the supply he needed. Likewise, gravity chutes allows the disposal of completed parts within the normal work area, eliminating the long movement to do so. So gravity chutes make clean work area possible as finished material is carried away from the work area rather than stacked up all around it. So basically, gravity chutes are the carrier which carried away the materials going the finished materials going to the stock room or the storage. area. So this is the example of a workstation utilizing gravity beams and belt conveyor to reduce reach and move time. So as we can all see, it has a five gravity beams in front of him, which being organized and filled with his all his supplies needed to create a to assemble a certain product. Then at the back portion, it has a belt conveyor in which he will put his finished materials, and the belt conveyor will transport the finished materials going to the stock area. So these are some examples of gravity beans and examples of gravity chutes. So I think that's all for this topic.
Arrange tools, controls, and other components optimally to minimize motion. Optimum arrangements allow users to access and use components easily and smoothly. The optimum arrangement depends on many characteristics, both human, their strength, reach, sensor, and task, the loads, repetition, orientation. Obviously, not all factors can be optimized. Careless arrangement can cause confusion and make things more difficult. The designer must set priorities and make trade-offs in the layout of the workplace. This figure shows the tool balancers provide fixed location for tools. However, certain basic principles should be followed. First, the designer must consider the general location of components relative to other components, using the importance and frequency of use principles. So these are the principles of display layout. The importance principle. Components most crucial to achievement of system goals should be located in convenient locations. The frequency of use principle. Components used more frequently should be placed in most convenient locations. Most frequently used displays should be positioned in the primary viewing area. The most important, as determined by overall goals or objectives or most frequently used components, should be placed in the most convenient locations. For example, an emergency stop button should be placed in a readily visible, reachable, or convenient position. Similarly, a regularly used activation button or the most often used fasteners should be within easy reach of the operator. Once the general location has been determined for a group of components, that is, the most frequently used parts for assembly, the principles of functionality and sequence of use must be considered. The sequence of use principle. Components which are used in sequence should be located next to each other, and layout should reflect sequence of operation. The functional grouping principle refers to the grouping of components by similar function. For example, all fasteners in one area, all gaskets and rubber components in another area. Since many products are assembled in a strict sequence, cycle after cycle, it is very important to place the components or sub-assemblies in the order that they are assembled, since this will have a very large effect on reducing wasteful motions. This figure shows a workstation utilizing gravity beams and a belt conveyor to reduce reach and move times. The conveyor in the background carries other parts past this particular workstation. The operator is feeding the conveyor from under the platform by merely dropping assembled parts onto the feeder belt. The designer should also consider using motors, systematic layout planning, or other types of adjacency layout diagramming techniques to develop a quantitative or relative comparison of the various layouts components on a work surface. So a systematic layout planning is a tool used to arrange a workplace in a plant by locating areas with high frequency and logical relationships close to each other. The relationships between components can be modified from traditional data on the flow from one area to another and should include visual links, eye movements, auditory links or voice communication or signals, and tactile and control motions. So this is an example of motor systematic layout planning. These principles of work design for workstations are summarized in the Workstation Evaluation Checklist. The analyst may find this useful in evaluating existing workstations or implementing new workstations.
Hello everyone, we are Group 10 and we are discussing Part 3 of Chapter 5, Workplace, Equipment, and Tool Design. So Part 3 is all about the principles of work design, machines, and equipment. So Part 3 has 6 topic outlines and we are going to discuss the first 3 topics, which is about first, take multiple cuts whenever possible by combining 2 or more tools in one or by arranging simultaneous cuts from both feeding devices. Second, use a fixture instead of a hand as a holding device. Lastly, locate all control devices for best operator accessibility and strength capability.
Place multiple cuts whenever possible by combining 2 or more tools in one, or by arranging simultaneous cuts from both feeding devices. For me, my topic is about how to use or apply the tools in a proper way in machine and equipment, or remove some materials from the workpiece in machine to make it right. And also we can use the feeding devices to facilitate the manufacture of products and also save time. Advanced production planning for the most efficient manufacture includes taking multiple cuts with combination tools and simultaneous cuts with different tools. And when we're talking about the advanced production planning, is about the allocation or raw materials, workers, and workstation to fulfill manufacturing order on time. And lastly, of course, the type of work to be processed and the number of parts to be produced determine the usability of combining cuts such as cuts from both the square, turret, and hexagonal turret.
So next topic to be discussed is using a fixture instead of the hand as a holding device. So if either hand is used as a holding device during the processing of a part, then the hand is not performing useful work. One example is when we did the two-hand process chart wherein it was stated that when the hand is only holding a material, then it is considered ineffective. That is why a fixture is designed to hold the work satisfactorily, thus allowing both hands to do useful work. So what is a fixture? A fixture is a work holding device to locate the work quickly and to support the workpiece properly and hold it securely. It varies in the design, so from simple to complicated devices depending on what is being manufactured in a certain company. So as I said earlier, a fixture is used in order for both hands to do an effective work. Fixture can differ on the complexity and design depending on what is being produced. It can be made of any hard material as long as it will serve its purpose accordingly. So before I will give a brief example, let me point out two advantages of using a fixture rather than hands as a holding device. So first advantages is it can save time in the whole process. Of course, there will be a longer and ineffective time when there is only one hand that is doing an operation while one hand is holding the workpiece. Whereas if you use a fixture, then you can use both of your hands to do the work, lessening the time of the activity because there is a fixture that can hold the certain workpiece or product. Next is it permits better quality in that the work can be held more accurately and firmly. So why is that? A fixture, as we all know, is a fixed device. We cannot deny the fact that when we use our hands to hold the workpiece, we tend to shake because it is our reflexes. Our hands are not stable enough to hold the workpiece. On the other hand, while the dominant hand is doing other operation, that is why when we use a fixture, it is already fixed and steady, and it can securely hold the workpiece without it being shaken, thus a more accurately end product. So an example will help clarify the principle of using a fixture as opposed to the hands for holding work. So the example is a company that produced specialty windows needed to remove 0.75 inches wide strip of protective paper from all four edges or corners of both sides of Lexan panels. So here is a flow process in producing Lexan panels using hands as a holding device. So first process is that an operator would pick up a single sheet of Lexan and bring it to the work area. So in this process, the operator is doing every operation manually. Next is the operator would then pick up a pencil and square and mark the four corners of the Lexan panel using his dominant hand while the other hand is holding the Lexan panel. Third operation is that the pencil and square would be laid aside or set aside, and a template would be picked up and located on the pencil marks, still using the dominant hand while the other hand is holding the Lexan panel. Lastly is that the operator would then strip the protective paper from around the periphery of the Lexan panel while his other hand is still holding the Lexan panel. So as you can see, the operator, or as you can imagine, the operator is doing the whole process manually. His dominant hand is doing the effective work while his non-dominant hand is doing the ineffective work because it is only holding the Lexan panel. It takes a longer time, a hassle, and a non-effective quality or non-excellent quality of a product. So this process has a total time of 1.063 minutes per piece. We can compare it to producing Lexan panels using a fixture. So the first process is that the worker picked up 3 Lexan sheets and located them in the fixture. As you can notice, it is already advantageous to use a fixture instead of just hands as a holding device because in using a fixture, it can accommodate 3 Lexan sheets simultaneously, whereas in just hands, the operator will do it manually. So after the 3 Lexan sheets is put in the fixture, the operator can strip off the 0.75 inches wide protection paper around the periphery using both of his hands freely because the fixture is already holding the Lexan panel. And then the sheets were turned 180 degrees using a hinge from the fixture. And then the protective paper was removed from the remaining two sides using both of his hands. So it has a total time of 0.46 minutes per panel or piece. So as you can notice, we have saved 0.603 minutes of direct labor for the operator per panel. So, which it is a save time to do more pieces. It not only saves time, but it surely improves the quality of the panels, and there will be an increase of production in a day. So here is a graphic image of the fixture for stripping 3/4 or 0.75 inches wide protection paper around periphery of Lexan sheets. So the fixture consists of a lid and a hinge. So as the operator put the three Lexan sheets, the lid will serve its purpose to hold the sheets so that the operator can freely use his hands to strip off the protective paper in the first side. After stripping the first side, the hinge will turn the fixture into a 100-degree angle so that the other side will be stripped off. That is all for my topic, and we can now proceed to the next.
So the next topic is to locate all control devices for best operator accessibility and strength capability. So we already know the principal objective of methods engineering, right? It is to improve productivity and decrease the unit cost of output while maintaining the health and safety of the worker. So this is relevant to our discussion because it deals with the man-machine relationship. Since the facility designer neglected numerous human factors, many of our machine tools and other instruments are mechanically perfect but incapable of effective operation. So what is meant by human factors then? So human factors focuses on how systems work in actual practice, with real and fallible human beings at the controls and attempts to design systems that optimize safety and minimize the risk of error in complex environments. In order for us to better understand what is human factors, let's have the gas Charles to continue.
Okay, so in continuation, we have here many of our machine tools and other devices are mechanically perfect yet incapable of effective operation because the facility designer overlooked various human factors, such as we have the first one, hand wheels, cranks and levers should be as such a size and placed in such positions that operators can manipulate them with maximum proficiency and minimum fatigue. Next, we have the frequently used controls should be positioned between elbow and shoulder height. Next, we have the seated operators can apply maximum force to levers located at elbow level. And last, standing operators to levers located at shoulder height. Next, we have here the forces to be exerted. For example, for a 10 to 15 pounds or 4.5 to 6 kilogram, force is like a diameter should be no less than 0.5 inches or 0.6 centimeter and preferably larger. For 15 to 25 pounds or 6.8 to 11.4 kilogram, a minimum of 0.5 inches or 1.3 centimeters should be used. For 25 pounds or more or 11.4 kilogram, a minimum of 0.75 inches or 1.9 centimeter. Diameters should not exceed 1.5 inches or 3.8 centimeter. The grip length should be at least 4 inches or 10 centimeter to accommodate the breadth of the hand. Next we have the guidelines for crank and handwheel radii. We have for the first one, light loads, we have the radii of 3 to 5 inches or 7.6 to 12.7 centimeter. We have the medium to heavy loads, radii of 4.7 inches to or 10.2 to 17.8 centimeter. We have also the very heavy loads, radii of more than 8 inches or 20 centimeter, but not in excess of 20 inches or 51 centimeter. We have the knob diameters of 0.5 to 2 inches or 1.3 to 5.1 centimeter are usually satisfactory. Lastly, we have the diameters of knobs should be increased as greater torques are needed. We have here the illustration as an example. The first picture is when using handheld tools, the wrist should be kept as straight as possible. So we have here the figure shows correct, which is the letter A picture, and the incorrect use of two types of rotating tool. So illustration here, picture A shows the incorrect one and picture B shows the correct one. We have also here the next example, picture A as an incorrect one and the picture B as the correct one. Correct location of hand grips on tools avoids having to bend the wrist. Next, we have picture A as the incorrect and picture B as the correct one. We have here the lifting with a bent trunk and a large horizontal distance between load and lower back. Picture A is more hazardous than lifting with the back straight and a small horizontal distance between load and body. We have also here other examples of work postures where there are problems with extreme joint angle, large muscular force, high degree of repetition, or high contact pressure. So these are this is important to manage fatigue. So why is it important to manage fatigue? One of the most important benefits is that proper fatigue management can lower the rate of accidents that occur by positively impacting the rate of human error and reducing it. It also increases the rate of productivity in several ways. So that's all for the first part 3 of chapter 5. Thank you.